Alright, welcome back. This is 6.5, the section on work. This is problem number 3, and probably the most important thing to put out there before we start this problem is the formula for work, which in integral form looks something like this. Work equals the integral of force dotted with an infinitesimal segment of length. Now, for example, if you were to pull, so I want you to imagine that if you were pulling with a constant force, we could pull the force out front, right? So work would equal F and then the integral of 1 dr, which this would, the integral of 1 dr with respect to dr is, of course, just r. So one of the formulas for force is F times r, and this is kind of a simplified version. This would work in the scenario where you are pulling something with a constant force over a certain distance. So let's say that we pulled this box with a certain force from point A to point B, and the force never changed throughout that period. Well, then the formula for force would simplify to this. But calculus, what's neat about calculus is that we don't need it to be a constant force, because we've been learning how to integrate things that occur under different conditions. So this problem in particular is very good at showing one of these cases. So the problem states that you have a length of rope. I'm going to draw my length of rope, and I'm going to say that it's got a certain length to it. And imagine that you're on a cliff. So this is you, and you're going to pull up the rope, right? You're going to pull up the rope, and what is given is we're given the length of the rope is 50 meters, and you've got to pull the whole length up. And this lambda thing here stands for a linear force density, given in newtons per meter, which is how much force each meter of rope is pulling down with. So it's like a density, a force density. And so as you can imagine, when you first start pulling the rope up, and you've got a whole 50 meters going on, the thing's going to be a lot heavier. And as you keep pulling up the rope, there will be less length of rope that will be pulling against you because of the linear force density. So as we start pulling this up, you'll have to apply less force, right? So now force is not a constant, so we can't pull it out of this integral. So now we have to set up an integral that's going to help us solve how much work will this individual do pulling this rope up. Alright, so to start out, let's figure out what force is. Alright, so the force of, for example, this rope at first is going to be the length of the rope times the linear force density, right? Because the length is in meters, the linear force density is in newtons per meter. Well, meters will cancel with meters, and you'll end up with force. So the force here is going to be the linear force density times the length. But as we discussed earlier, as we pull up the rope, we lose some of the length, and thus there is less length, and therefore less force. So what we're going to go ahead and do is we're going to say that force is equal to lambda, the linear force density, and then we're going to say 50 minus whatever the length of the rope is. And the reason why we say that is because when you start out at 0, you've pulled up 0 length of the rope, then you're going to have the full lambda times 50 meters. But as you start pulling up a meter of rope, now you have 50 minus 1, that's only 49 meters of rope that are going to attribute to the force downwards. And so this is the setup. The next step is we can go ahead and say, let's go ahead and call L x, because we're so used to working with x as a variable. And you'll notice that the direction, or the r vector, the direction in which this is pointing, is going upwards. And that's also, if we're calling L x, the direction of travel is also on the x-axis. So here we can go ahead and say that force is equal to the linear force density times 50 minus x. So now we can go ahead and plug this into this formula and say that work equals the integral of the linear force density times 50 meters of rope minus however far you pulled up the rope with respect to x. Because we're calling this the x-axis, and therefore the segment of motion is, or the displacement is, how the rope's being displaced is pointing in the x direction. Now the question is, how do we pick our boundary? Well, we want to start off with 50 minus 0, right? Because we have the full 50 meters of rope to start off with. And by the time we're done, we want x to be 50. Because once you've pulled up all 50 meters of rope, then you're going to have 0 force opposing you. And so we want x to go from 0 to 50. And so that's the setup. You'll see up here that lambda is equal to 0.75 newtons per meter, so we'll go ahead and fill that in. And so now it's a pretty straightforward integral. We can pull out the 0.75 because it's a constant. We're going from 0 to 50 for 50 minus x dx. Linearity allows us to take the, well, I guess they call it the addition rule or something like that, but because this function is linear, we can take the integral of this separate from the integral of that, and then just keep them together. So the integral of 50 with respect to x is 50x. The integral of x is going to be x squared over 2, and of course there's still a minus sign here, so we leave it. And we're going from 0 to 50, multiplying it by 0.75, and that's going to give us our quantity of work in joules. And so now it's just mainly a plug and chug problem. So 50 times 50 is 2500 minus, when we plug in 50 for x, 50 squared divided 2 is 1250. Now we're going to plug in 0 for this formula, and of course 0 times anything is 0, and 0 times anything is 0, so this second part is just going to be 0. We still have to remember the 0.75 constant that we pulled out. And let's figure out, so 2500 minus 1250 times 0.75 is 973.5 joules of energy. So that's how much work that we had to do to drag this rope up, the whole 50 meters of it, with a uniform linear force density. That's how much energy and work it took to pull this thing up from the cliff. So I hope this was helpful, and I'll see you next video.